Example 10.4, looking SAT. Actually, these are old SAT, the way it used to be set up, and ACT scores. Suppose the distribution of scores on the SAT exam is normal with a mean of 1500 and a standard deviation of 240, while the distribution of scores on the ACT exam is normal with mean 21 and standard deviation of 6. Now, part A asks us to draw a well-labeled sketch of these two normal curves. Remember, a normal curve is bell-shaped and symmetric. So let's start with the SAT. We want to make sure we label the axes, the x-axes in particular. You're going to notice that mine's not perfect. They don't have to be perfect. I know my center's at 1500. This is the SAT scores. We also want to label what the standard deviation is somewhere, and I'm going to put that right here. I also am going to write out what this is. This is a normal with center at 1500 and standard deviation of 240. There you go. Please do the same thing. Come back and check your answer for the ACT. So hopefully you paused, took a moment, and did that drawing. And I should have put SAT score, by the way, instead of scores, just because we're recording individual scores as we go along. So part B, about 95% of SAT scores fall between what two values? I'm going to first of all say, when you're doing these problems, it really helps to draw a little picture. Doesn't have to be perfect, but drawing a picture does help quite a bit. So if I know, for instance, that I need to be, let's see, my center is at 1500, and I need to be to have 95% in this area here. And this is going to be 95%. What did we learn with the empirical rule? We learned that 95% of observation fall within plus or minus 2 standard deviations of the mean. So if I take, let's see, 1500, and I'm going to do plus or minus 2 standard deviations. If I do the calculation out there, I'm going to get 1020, between 1020 and 1980 is where 95% of the scores fall between. I do suggest as you work these, say, okay, 1500, I'm going to do the plus 1 first. This is plus 480. And then write out your answer. I would, as I did this, just writing them out quickly, I'm assuming your math is strong and you know to always write when we do intervals from low to high. Please take a moment, pause the video, and do the same thing for the ACT scores. Hopefully you got between 9 and 33. Now let's look at a different sort of case. Suppose that Barb scores 1740 on the SAT. About what percentage of SAT takers scored higher than Barb? Explain, and what percentile is Barb's score at? So first of all, I'm going to say already. We know that the center is at 1500 and Barb scored at 1740. Okay, cool. And we're wondering, it says what percentage scored higher than her, so we're interested in this. So this is the higher part. The percentile is all, she did better than what percentage, and that's the percentile. So we would need the other side here. What do we know about the dash side? If we know the star side, what does the other side have to equal? Well, that's that complement rule. It'd have to be 1 minus whatever the value is for the star. So let's see, we don't have anything like a z-score yet. So if you've taken statistics before, probability, you may be like, well, why don't we just do a z-score? It'd be faster. We're getting there. But first of all, I'm going to say, okay, she's 1500. Let's see what happens if we add 1 standard deviation. And that's 1500 plus 240, and that gets me exactly to 740. Cool. You're like, all right, well then where do we go from here? I'm going to change colors so hopefully it'll be clear. We know that plus or minus 1 standard deviation here covers 68%, right? But the answer is not 68 because remember, we want to know what's in this tail here. We want to know what's right in here. You may be thinking, well, I don't really know where to go from here. Well, we know overall that there's 100% in the tail, or 1. 100% minus 68% leaves us with what percent? And hopefully you think, oh, that leaves me with 32. Okay, so between these two tails, which are symmetric, there has to be 32%, or 1 minus 0.68, which would give us 0.32. So I know that the 32% divided by 2 has to be in this tail, and 32% divided by 2 has to be in this tail. So what do we know now? Suppose what percentage scored higher than Barb? Well, we know that 16% scored higher than Barb. What percentile Barb? Well, Barb did better than everyone because she's above this everything down here. The easiest way to do that is to see it with the complement rule. Say, well, okay, we know that she didn't do as well as 16%, so she must have done better than 100 minus 16%, which gives us 84%. So she's in the 84 percentile. Okay, part C. Suppose that CC scores 30. Who's done better compared to their peers, Barb or CC? And it says, explain. Well, CC took the ACT, and that's centered at 21, and it has a standard deviation of 6. So we know that Barb did exactly 1 standard deviation better. So 1 standard deviation, remember sigma is 6 in this case, so 1 standard deviation better would be 27. But we know that CC scored 30. So who did better, relatively speaking? Well, CC, excuse me, is farther in the tail. So CC scored more than 1 standard deviation above the mean. On the other hand, Barb only scored 1 standard deviation above the mean. So CC did better. She's further in that tail. Suppose that Reese scores 1020. About what percentage of SAT takers scored higher? Once again, we know the center, we're told, is at 1500, and he did down here at 1020. So we know we're going to have to take some standard deviations away, so to speak. We know that we're going to take 1500, and let's take away 1 standard deviation and see what we end up with. And we get 1260. Well, that's not as, he did lower than that, so let's take away another 240, and we get 1020. Oh, okay. So he's 2 standard deviations below. So 95%, based on that empirical rule, fall in here. Based on what we did before, we know that the 5% that's left over, because remember the area under the curve has to be 100, that in each of these tails is going to be the half of the 5%, in other words, 2.5%. So what percentage scored better than Reese? Well, the 95 plus the 2.5 gives us 97.5%, scored higher than he did. On the other hand, if Sally scored 12 on the ACT, who's done better compared to their peers? Well, we've got, let's see, she's at 12. If we take away 2 standard deviations, we're going to end up with 9. So 9 is 2 standard deviations below, which is what Reese was. But Sally did better than that. So who scored better? Sally did. Sally scored better compared to her peers, as she did better than 2 standard deviations less than the mean. Cool. Now, this is really nice if you can get it to work out exactly as we did in this example, but what we're leading to is something called the z-score. It's a standardized score. What it does is it standardizes the number of standard deviations we are away from the mean. So here, very important, a standardized score, also called the z-score, for an observation is found by subtracting the mean and then dividing by the standard deviation. It's useful, especially if we're not exactly one, two, or three standard deviations from the mean. How we calculate this is we say z, this score, this is how far we are from the mean, y minus mu over sigma. Now these are the normal center, the normal's standard deviation, and this is the observation. Let's calculate it for everyone. Calculate the standard score for each student, who has the highest and who has the lowest. Well, we know that Barb scored 1740. We take away the the center, divided by the standard deviation, and we got 1, which makes sense because that's what we found before. Reese, on the other hand, what number would you expect? Would you expect a positive 2 or a negative 2 if I told you it was 2? And hopefully you think, oh, it has to be a negative 2 because he's below the average. Oops, here we go. He's below. Let's check that. And we get negative 2. I'm going to leave you to calculate these. Cece is 1.5, and Sally is minus 1.5. So who, relatively speaking, when we're looking at just these numbers, who has scored the highest and who scored the lowest? Well, the lowest was Reese because he was 2 standard deviations below, and Cece was the highest because she was 1.5 standard deviations above. So this standardized score allows us to compare directly. So normal distribution calculations define the area under a normal curve under a certain interval. We're going to use the z-score that we have. We're going to standardize by subtracting the mean and dividing by the standard deviation. So this is the standardizing step. This is the z-score, which indicates the number of standard deviations below or above the mean. Then we're going to use a table where the center is at mu and the standard deviations are each 1 of normal probabilities, which give us the area under the curve to the left of the z-score. And we're going to practice with that. You can also use an applet or a formula, but in this class, I'm going to always refer back to the table, and we'll work with that in just a few moments. One thing I get is, can z be 0? I frequently ask that question in class, and the answer is yes. Why? Because y can equal mu. If y equals mu, then they're the same value. If we think about it, if y equals mu, we're going to be right in the middle. What would we expect to have on either side? And hope you're like, well, it'd be 50% and 50% because this bell curve is symmetric around the center. One thing I also want to caution you is it always is positive being above always better than like being below. The example we did with these scores, it's better to have a higher score, but there are things that it's better to be lower on, like blood pressure. Would you rather be at the high end of the tail? Not super low, but the high end of normal or the high end of high or the low end of high. You definitely want to be at the lower end of high. So make sure you're careful with context throughout these problems. And next, we will start working with the tables.